In this video, this is one of two in the Chapter 2, Unit 2, Lesson 1. This is on secant and tangent lines. This is going to cover the topic, one big idea in calculus of finding the instantaneous rate of change, or the slope, at a single point. There are two big ideas in calculus, and finding that slope or rate of change at a single point in time is one of the two big ideas. The other is area under the curve, and we'll talk about that one later. Okay, so let's look at this graph. This is just a generic function, f of x. And you can see that there are two lines drawn in this function. The first is a secant line, and that secant line is a line that intersects a function at 2 points. So we can see that when x is a and b, so we have those two x values, the secant line goes through 2 points, f of a and f of b. And a tangent line, the red line, is a line that intersects a function at exactly 1 point. So in our case, the 1 point is at this value x. Okay, so the question here is, how do we find the slope of that tangent line when all we know is one single point? Well, let's look at that secant line. In order to find the slope of a line, we know that slope, let me use blue because we're talking about the secant line. We know that the slope of any line is the change in y over the change in x. And in our case, with this specific example that I have drawn for you, the slope of the secant line that I have up above has two specific points. So the slope of that secant line that we have up above is y2 f of b minus y1 f of a all over b minus a. Change in y over change in x. But if we look at the tangent line, if we try to find the slope of that tangent line, we have a bit of a problem because we only know one single point on that line. And that point is x comma f of x. That's all we have. We don't have a second point on the line that we know in order to find the rise and the run, or the change in y, change in x. So that's where this unit comes into play, is how can we find the slope of that line if all we know is 1 point on it? So what's that instantaneous slope? Okay, I've redrawn this function down below, and I'm going to put that tangent line back on there. So I'm going to draw my tangent line back on here. It's approximately where it was. So what we're going to think about is, there was a purpose for me drawing that secant line. What we're going to think about now is how can we use that secant line to determine the slope of the tangent line. And this is one of the big ideas of calculus, where they started to think, okay, how can we do this with what we already know? Well, right now, the slope that was given up above, the slope of that line, that secant line, is not even close to the slope of the tangent line. The only thing they have in common right now is that the slope of this secant line is positive and the slope of the tangent line is positive. But as you can see in this graph, the tangent line slope is much steeper than the secant line slope. Okay, so let's try a different secant line then. What if I chose a secant line whose points were a little bit closer together? So if I draw the line secant to that function, in other words, the line passing through those 2 points, that wasn't very good. Let me try again. We can see that we're getting closer, that the slope of this secant line is getting closer to the slope of the tangent line. So let's see if we can get even more accurate. Instead of choosing 2 points on either side of that point of tangency, let's use the point of tangency, in other words, the point where the tangent line touches the graph. Let's use that as either f of a or f of b. So here's the tangent line again. So instead of choosing f of a and f of b around that, what if, oops, I need red again. What if I used this point as one of the points on the secant line? That seems pretty good. And then I choose a point that's really, really close to that. This is not to scale, but assume that those points are really, really close to each other. Then I can see that this secant line becomes almost the same as that tangent line. Okay, so let's see if we can do this in a generic way. So let's talk about this as in the general sense. So we're going to generalize this idea. So I'm going to use this first point. This first point was the point x comma f of x. Now this second point, I'm going to put it out here because it's going to need more space. This second point is going to be really, really close to the other one. And what we say is, I'm going to draw these in here. What we say is, and you saw this in the last section, in the last unit, is that this little space in between the 2 points, we're going to call that delta x. You saw that before. We were just manipulating delta x without actually using it. So that little space in between these 2 points on the secant line, let's call it delta x, or the change in x. So what that would mean then is that this second point is at x plus that small little change in x. So that means this ordered pair right here, here's the x value, and the y value is this. Okay, so in order to find the slope of that tangent line, we can start to use this idea of these 2 points being close to each other. So let's look at the slope of the secant line first. Slope of the secant line, because we have 2 points on the line. The slope of the secant line is y2 minus y1 over x2 minus x1. Does that kind of look familiar? What if we simplify the denominator just a little bit? This is probably going to look familiar to what we did in the last unit. So now we've got f of x plus delta x minus f of x, and then the x's will eliminate each other in the denominator, leaving you with just delta x. We worked on that in the last unit. We did some problems that had f of x plus delta x minus f of x. But this hasn't solved our problem yet. This is the slope of the secant line. That secant line has 2 points on it. The tangent line only has 1 point. So let's think about limits. I'm going to pause here for a second. I want you to pause this video. How do you think limits are going to come into play in this case in order to find the slope of that tangent line? Pause now. Okay, welcome back. I hope you thought about limits a little bit, because the key here is for this delta x, the space in between those 2 points, to basically disappear. So we want this delta x to approach 0. That's our goal. If that space between those 2 points on the secant line gets so close to each other there's almost no space between them, now we have a tangent line. So here's where the limit comes into play then. Slope of the tangent line we call this a derivative. Can be found by taking the limit of that slope as delta x approaches 0. So as the space between those 2 points gets really, really close, that space starts to disappear, we end up with a line that is tangent to a curve. You saw this in the last unit, and I told you it had something to do with slope, but this is where it comes in. So f of x is the function. We say that the slope of that tangent line, we call that f prime of x. So you're going to be using these words, these symbols interchangeably. So I can say the derivative, and we use f prime of x to say that's the derivative, that's our shortcut, equals the slope of a line tangent to the curve, and one way to find that is by using this limit. So all of these things are the same. These are all synonyms. I'm going to say them over and over and over again interchangeably so that you realize that every time we're finding a derivative, every time we're using this limit definition, every time we're finding the slope of a tangent line, every time I say f prime of x, those are all exactly the same thing. It's really important that you're visualizing what you're doing when you're finding this limit or this derivative or the slope of the tangent line. Okay, I think this is a really good place to pause. And in the next video, we're going to use this idea to learn a little bit more about a function.